All right, so let's take a look here. We've got where'd it go? Here it is. A rolling object has a mass and speed. Its moment of inertia about its center is I, and its angular speed is omega. What is the total kinetic energy? So what we're checking here is, you remember that we have kinetic energy translational, and then we have kinetic energy rotational. Why can I not write today? Okay, so the translational is 1/2 mv of the center of mass squared, 1/2 mv squared, and the rotational is the 1/2, and what's like m? I. What's like v? Omega, so omega squared. So this is really kind of just a plug and play, but making sure that you're starting to make the connection between translational kinetic energy and rotational kinetic energy. So the mass is 6 and the speed is 4. And this is going to give me kilograms meters per second, meters squared per second squared, plus 1/2. Why isn't that doing that? 1/2, and then it's giving me 1.2, and this is going to be kilograms times meters squared, and then omega squared, so that's 5 squared. So that's radians, which doesn't really have a unit, divided by second squared. So look, the units are the same. This is kind of bonzo. And at this point, I just have to do the multiplication. Okay, so I have 0.5 times 6 times 16 plus 1/2 times 1.2 times 25 times 25. I can't write on the edge, so it doesn't like my 2. 25. All right. And so the total kinetic energy of that would be, whatever that says now I can't see it, would be 63. That's it. So the total kinetic energy here is 63 kg m squared per second squared. Dunny bunny, certainly awesome. Okay, now rotating disk has a moment of inertia and an angular speed of omega equals 8 rads per second, and obviously I'm getting there, but it's all over the place. Come here, little silly thing. Okay, so we have a rotating disk has a moment of inertia of 3. Now remember, the bigger these are, that means the more mass is away from the center, meters squared, and angular speed omega equals 8 rads per second. What is its angular momentum? Actually, this is an easy one. I don't know if I include it in the lecture or not, but I don't know why it's calling it L. Angular momentum, oh yeah, because your book calls it L. And your dynamics book is going to call it H. So I'm just going to write angular momentum equals I omega, just like linear momentum. Yeah, we did kind of talk about this, but just about real linear momentum is mass times velocity. So again, you're seeing that mass goes to I and V goes to omega. So really this is just 3 times 8. So it's 24 I omega, angular momentum, 24 kg m squared per second. So that one's not bad. Let's see. Calculating object has angular momentum. I'm just going to get rid of that L. Angular momentum is 18, and that's equal to I times omega. Now these are if they're rotating on their axis. That's whenever it's I times omega. It can, if it's rotating and rolling, then you've got multiple things going on. So right now we're just going to be rotating on an axis. So maybe I should even write that on an axis has angular momentum of 18 and a moment of inertia I. What is its rotational kinetic energy? Okay, this is like 2 steps. So I have 18 equals 2 times omega, so omega is 9, and its rotational kinetic energy is 1/2 I omega squared. So 1/2 2 times 9 squared, so that would just be 81. 81. Easy peasy. So again, we're just trying to help you start to get the idea that things that are moving in circles aren't super different from things moving in a straight line. They're just, I mean, they follow the same general basic properties, where if you kind of already know what's going on with linear stuff, then going to angular stuff isn't infinitely worse.